Yes, so when we look at this cone, all right, so look at it. This is a two-dimensional view of a cone being fitted on the earth. Are you okay? So we are putting it on it like that, and it's going to cut it. It's going to touch it at one latitude, at a latitude phi 1. Are you okay? Okay, so I don't want to go into the mathematics of it, but the angle at the top of the cone, the apex, are you okay, also determines, is used in the calculation. So later we'll find out that if you actually increase the angle at the apex, you end up having a flat surface, but it's not really part of this. I won't ask you a question on that, so let's not waste our time. All right, so we can also have a situation where we have the earth surface, but then in this case, it cuts it. Are you okay? So it cuts it at 2 points. What it means is that the distortion is minimized. Okay, because we said that if it actually touches it, the error is minimized. Is that not so? So what if we cut deeper? You get that? So it makes a lot of sense to do this. Then in that case, it becomes more accurate. Okay, the conical projection becomes more accurate when it makes use of two standard parallels. Pronouncing that word is really a challenge, isn't it? Two standard parallels. You need to eat some okra before you pronounce this word. Is that not so? So two standard parallels. Right, so we can now call that Phi1 and then Phi2. All right, with the angle at the apex. Okay. But the concept is all I want you to know. I want you to understand that we can project onto it and then write a formula. Okay. Now that formula can now be integrated into software so that when you bring your data, you can decide that, okay, I want to take this GPS data, WGS84, longitudes and latitudes, and I want to convert it to Albert's conical conformal projection. That when you are looking at it in the software, because you've been taught, you kind of appreciate it. So some of the things you are taught is just so that you become more familiar with something, not because we want you to write any formula or come out with a new idea. Okay, so two standard parallels are being depicted and shown on the board. Okay, so now you've learned a few keywords: meridians, parallels, longitudes, okay, latitudes, North Pole, South Pole, distortion. Are you okay? Another thing we want to learn is the datum. Is that okay? To know about a datum. A datum is like a reference surface. So if you measure height at a point and you say this height is so to 20 meters, you haven't said anything. It's always with reference to a datum, a reference surface. Okay, so one of the surfaces that we are so familiar with will be the mean sea level. Are you okay? The mean sea level. Now the mean sea level, what is it? The mean sea level is like, if you ask me, I'll just say measure the height of the sea and then take an average of it. Yes, exactly what is done. Okay, so there are measurements that are continually being done, and they've been done over years. Are you okay? To determine the mean sea level, and there's a correction that is applied because you see, the sea levels are controlled by the presence of the moon and the sun and all that. So you can imagine that it can't be a constant figure. So that correction is applied always when levels are being taken. Is all right? Now, when you actually extend the mean sea level, when you extend it, you get a surface called the geoid. Okay. So just take the mean sea level, okay, go to the shore, measure it, and then imagine it. So mathematically extend it around the earth. You end up with a shape which is not regular. Why? Because it's subject to gravity. Are you okay? The sea levels are subject to Newton's laws of gravitation. Are you okay? So obviously we can have a funny shape instead of having the regular shape, and it's subject to all the Earth's mass, depending on the rock densities at a particular place. You have a certain pool. Are you okay? Because remember that the law of gravity deals with the masses. Are you okay? All right. So, but then the Earth we said is round, isn't it? And we can approximate it to a spheroid. All right. Or if you like, we can look at it in terms of a sphere, something close to a sphere. So we have two surfaces: the geoidal surface, then we can have the spheroid. Are you okay? Okay. Based on which, of course, anytime you're dealing with WGS 84, longitude and latitude coordinates that your GPS is giving you, your phone is giving you right now as we are talking. Someone is on his phone. Okay, your location is on. That data you are getting is actually latitude and longitude, and this is based on a certain surface, spherical surface. Are you okay? Which is actually longitude and latitude. So we have the geoidal surface, okay, that you can measure with reference to, and you can also measure with reference to the geoid. Are you okay? All right. So when we talk about datums, then that's what we are actually referring to, reference surfaces. You can have your own local datum that you actually measure from, are you okay, or measure to. So let's take note of that. Okay. That's it. I don't want to take it any deeper than it needs to, but it tells you that you can actually have other surfaces that can be defined, but basically this is it when it comes to heights. Okay, so you talk to any surveyor, they talk to you about autometric heights, you talk about geoidal heights and all that. That's what they're actually referring to. You need to know that as an engineer because you are building, isn't it? Okay, all right. So now we will now talk about the UTM. So what is the UTM? And I'll tell you a funny story and make sure you don't become a victim. Is that okay? At the end of this story, where I asked a question about UTM in exam, and then someone, Googled it. Okay, so I've warned you about using Google, haven't I? And then the result that he got was something else. Are you okay? And he was so convinced that was the answer to the question. In fact, the whole question was to find out if the person was coming for lectures, to find out if the class, if anybody. So the victims were people who were not attending lectures. So he got something funny. I don't remember exactly what it was. I don't know whether umbrella transformation, something funny. And then he explained, but that was a big zero. Yeah. Don't be a victim. Always
universal
make sure you're in a lecture for your own good. Universal something. A person wrote something. I don't. It was funny. I was so disappointed and sad. Yes, Christian. And I was so disappointed and sad. I won't lie to you. And he was busy explaining it with diagrams. Okay. All right. Yeah, it shouldn't be the case. It shouldn't be the case. UTM stands for Universal Transverse Mercator. Okay.
Mercator.
I would say write it down. Okay, I'm not a motivational speaker. I can be. Write it down.
So is it MERCA?
Christian, you said?
Is it MERCA?
MERCATOR. Yeah, let me write that again.
Oh,
I think. Right.
okay.
Of course, you're going to get a note, so that's why sometimes. Okay. MERCATOR. Transverse is transverse, universal is universal. Okay, so Mercator is the name of a human being. So, I mean, you just put it there. Universal means, around the earth, more or less, like everywhere you are. Universal. Are you okay? People use the word universal. It doesn't mean they're traveling to space. Are you okay? Transverse, we all know transverse. It means we are making use, transverse means we are making use of a cylinder or a developable surface, which is actually whose axis is perpendicular or orthogonal to the axis of the earth, the axis of rotation of the earth. Are you okay? The earth revolves around its axis. It turns. Are you okay? So it's always going like that. Like GTV has been showing the earth over there. I don't know if they stopped showing the rotating earth. Are you okay? So universal trans. So what is it? What is it? It's a projection. It's a very popular map projection coordinate system. Are you okay? Map projection. Right. Why is it popular? It's popular because it's universal. You can actually use it anywhere. Are you okay? It reminds you of this way. There's an advert on this way. So you can eat anywhere, anyway. So that's how UTM is. UTM, is very, very good for anybody that's doing any work in engineering and all that. Why? Because it's pretty accurate. Okay. So let's talk about some qualities of the UTM. Like I said, it makes use of a cylinder. Okay, so it's a cylindrical projection. Cylindrical projection. The UTM also makes use of a zonal system, or makes use of some zones, a number of zones. So it divides the Earth into a number of zones. Okay, so 60 zones. So if you draw the Earth and you divide it up into 60 zones like that, can you imagine if this is zone 1 and then zone 2, and then you are going on and on and on, and you come back and you have 60 zones. Okay, so that'll be 59. Okay, after you've gone around and come back. Okay, sorry, I'm not drawing this very well. These lines are supposed to meet at the North Pole. Yeah. So the North Pole is up here. They're all meeting up there. Okay, so if you have 60 zones, divide the Earth into 60 zones, 60 strips. Are you okay? Starting from one point and coming back to the same point, then what is the width of every zone? So that question goes to the class. I want an answer. Mention your name, and then you answer it. Because maybe your name will stick and then it will give you some favor. You never know. I'm the boss now, isn't it? So I'm favoring people. Yes, anybody with the answer can mention your name and give me the answer. What is the width of every zone if you have 60 zones around the Earth? Start at a point and come back to the same place. If you divide the Earth into 60 zones, what would be the width of every single zone? I want an answer from the class. Mention your name, then you tell me.
Loser, can I try?
You get what?
Can I try?
You can try, yes, of course. Nanaya. Is it Nanaya, right? Okay.
Yes, please.
Okay, go ahead, yes.
Yeah, it's 66.
You get what?
I got 6.
You got 6. Okay, I think you are right. Let me check it up. 360 divided by 60. Yeah, you're right. Yeah, Nanaya, well done. So you're getting 6 degrees. Okay. So let's not forget the units. You are getting 6 degrees. Okay, thank you very much. So every zone is 6 degrees. Of course, 6 degrees is like a huge distance, and like it's kilometers. Are you with me? Like thousands of kilometers. So don't think it's like some small thing. It's really a large exponent. Okay, all right. So let's say more about the UTM. So 60 zones, it has distortions at the central meridian. So every zone, there are values. Okay. So to define your coordinate system for UTM, you have to first determine your zone. So Ghana, for example, is in zone 30, between zone 30 and zone 31. Okay, for UTM. So you have to also define your hemisphere. So Ghana is in zone 30 north and then zone 31 north. So like it shares, it's between 2 zones more or less. So some part of it is zone 30, some part of it is zone 31 north. Okay, so you know why the north means that we are north of the equator. Are you okay? And those who are below the equator will use south. So you have to attach south to it. So 30 south, 31 south. Okay, if we were below the equator and yet within the same longitudes and latitudes. Okay. Okay, the handwriting gets beautifuler and beautifuler, doesn't it? Okay, so I guess it means I'm getting hungry, but we still carry on. We get a lot to talk about, a few things to talk about. All right, so 30 south, 30 north, and all that. What does it mean? Let me just depict it. So the Earth can be, divided up into two hemispheres: the northern hemisphere, and then we can have the southern hemisphere. Okay, so let me spell hemisphere. Hemisphere. It's like a sphere. Are you okay? All right. So north is actually here. Let me increase the width of my pen a bit. And then south is down there. Are you okay? All right. So we all know that Africa kind of has that shape where we have the equatorial parts of Africa. Are you okay? Being around this area. Okay. So you have to define that. And then once you've done that for the UTM, then it means something. What are the implications? So let's find out the implications. So in any particular zone, there's what we call the central meridian. Okay, so the distortion along the middle is actually 0.9996. Okay, and at the edges we have 1.0003. Okay, so the distortion is defined by a scale factor. Okay, so scale factor of 1. What does scale factor of 1 mean? If you understand it, you understand everything on the board. Can someone just tell me? Let me call someone. I think I have some friends here. Grace, you're my friend. Are you there? Grace. Grace is my friend, so I'm calling Grace. If Grace doesn't mind me, I'll move on and I'll assume Grace isn't part of this class and I'll move to another friend of mine. What does the scale factor of 1? What does it mean? So I'll move on to another friend. So Grace is not part of this class, even though I see her name here. Gotthold. Yeah, we are all friends anyway. I'm just trying to pick up on some people. Okay. Yes, Gotthold. Scale factor of 1. What does it mean? Scale factor of 1. So these are scale factors, but I want you to use that concept of scale factor of 1 to now understand what these mean. Yes, what is scale factor of 1? What does it mean?
Can I try, sir?
Say it again.
Can I try?
Try. Yes, mention your name and try.
It means that along that line, along that section, all the figures there are being multiplied by.
No. When someone says a scale factor of 1, what does it mean? That's the question. So answer the question. The question has an objective. Okay. Research questions relate to objectives. I think I'm in the mood, isn't it? Okay. Yes, carry on.
It means it's being multiplied by a factor of 1.
What does it mean as an engineer? Scale factor of 1. Anybody else? This is anyway. Let me caution all of you. This is a GHS question. What does it mean? Scale factor of 1.
The meaning that every distance that you measure, you multiply by 1.
Okay, that is the wrong answer. But I want you to I'm refreshing you. I know you've forgotten. So scale factor came into the teaching when we were being taught math, when the teacher at that JHS, wanted to talk about enlargement and reduction. Are you okay? So when you enlarge a shape, then you have a scale factor. Are you okay? The change is a change that brings about a scale factor. Otherwise, scale factor doesn't mean anything. It's irrelevant and it shouldn't be discussed. But the relevance of it is the fact that if you have a scale factor of 1, it means the object hasn't changed in shape, in size. Are you okay? So scale factor has everything to do with reduction and then enlargement. Do you remember some topic like that? Yeah, reduction and enlargement. That is what was at the center of it. Scale factor. So as you said, you didn't mention it, but as you said, the scale factor is a value that you multiply by something. Yes, so you are right in saying that. I shouldn't say you are totally wrong. You multiply it because a factor, isn't it? But obviously, you multiply it by a certain value only to determine whether it has been reduced or enlarged. So in this case, the accuracy of the UTM is determined by the scale factor at the central meridian and at the edge of the zones. Are you okay? And you can look closely at the values and see that 1.003 is approximately 1. And then 0.9996 is approximately 1. What does it mean? It means that we are not having a lot of distortion, but there is some distortion, right? So when you have an object which actually spans 1 kilometer, let's use that, it's easier, 1 kilometer, and then we use the UTM coordinate system, if you use the UTM to project the UTM projection. What's going to happen to the object? On the round surface, it's about 1 kilometer in length. After using the UTM, let's see what happens to it. At a scale factor of 0.9996, let's assume that the object is near the central meridian. You realize that we multiplied, as you said, Ben, or whoever said that, we multiply it 0.996 by 1 kilometer to find out the enlargement or the reduction. Are you okay? So we now get 0.9996 times 1,000 meters. Grace, are you back? Are you still
Hello, sir.
not part of this class?
Hello, sir.
Yes, Grace, where did you go to? Were you here?
I was in a noisy place. I'm traveling.
Okay, all right, I understand, it happens. Okay, so now, as you can see, we're gonna have a value. Let me just move this. I'm moving this window away. It's obstructing me. Okay, so now I'm going down to do this. So this will give us, just move this, 999.6 meters, isn't it? Originally it was, what was the length? 1,000, isn't it? So has it reduced or enlarged? Is it reduced or enlarged?
Reduced.
And by how much?
By just
0.4.
By 0.4.
Exactly. All right. So anytime you are working on a projection, you're working on a surface like that is round, then obviously you are subjecting your values to a certain error. But 0.4 in engineering, I know I've worked on a project where the accuracy had to be 3 millimeters. Can you imagine that? So this is like, oh my God, are you okay? It's not supposed to be accepted. So take note of that. But obviously, we are looking at very small scales. When you work at small scales, this is no error. Okay, but at a larger scale in engineering, you have serious issues. Okay, so the UTM, these are some of the characteristics of the UTM. Okay, it's based on a cylinder. It makes use of a zonal system. Okay, now let's talk about the coordinates. What sort of coordinates do you get when you use UTM? You get your coordinates are in meters. Always. Okay, take note of that. Why? Because there's a false northing, a false easting. Let's start with a false easting. If you done some basic surveying, when I write easting, you know what it is. The easting is like the X in the coordinate system and the Cartesian coordinate system. False easting of 500,000 meters. Okay, so that is the origin. Are you okay? So the origin for the UTM makes use of a false easting. The word